208 volts panel is considered a separately derived system. A separately derived system is defined as an electrical system that is derived from a transformer's secondary winding and provides power for circuits that are isolated from the primary system. It has its own neutral and grounding electrode system. According to the National Electrical Code, separately derived systems must be grounded and bonded. The system must have a grounding electrode system. The grounding electrode conductor must be sized according to the NEC. The grounding electrode conductor must be bonded to the transformer enclosure, the equipment grounding conductor, and any metallic parts of the system. The 208 volts panel is a separately derived system because it is powered by the secondary winding of the transformer. Therefore, it must be grounded and bonded according to the NEC requirements for separately derived systems. This means that it will require a grounding electrode system, grounding electrode conductor, and bonding to the transformer and equipment grounding conductor. When installing a separately derived system, several key considerations are necessary to ensure safety and code compliance. Firstly, the grounding electrode system is a critical component. This system typically involves connecting to a grounding electrode such as a ground rod, a metallic water pipe, or a concrete-encased electrode, often referred to as a UFO ground. The selection of the appropriate grounding electrode should comply with NEC section 250.52. The grounding electrode conductor, which connects the neutral point of the separately derived system to the grounding electrode, must be sized appropriately. NEC table 250.66 dictates the size of this conductor based on the size of the ungrounded conductors. For example, if the ungrounded conductors are sized to 3/0 American wire gauge or smaller and are copper, then the grounding electrode conductor should be at least number 8 American wire gauge copper. Secondly, bonding is essential to create a low impedance path for fault current to return to the source. This involves bonding the transformer enclosure to the equipment grounding conductors that serve the loads connected to the 208 volts panel. Bonding jumpers must be sized according to NEC table 250.102, which bases the size of the bonding jumper on the size of the ungrounded conductors. All metallic parts of the system, including conduits, enclosures, and junction boxes, must be properly bonded to ensure equipotentiality and minimize the risk of electric shock. Thirdly, overcurrent protection is another critical aspect of installing a separately derived system. The primary and secondary sides of the transformer must have appropriate overcurrent protection devices, such as circuit breakers or fuses, to protect the transformer and the connected equipment from overloads and short circuits. The sizing of these overcurrent protection devices should comply with NEC section 450.3. Fourthly, the neutral point of the separately derived system must be properly identified and grounded. The neutral conductor must be insulated and identified with a white or grey marking. It must be connected to the grounding electrode system at a single point, typically at the transformer. This connection ensures that the neutral is at or near ground potential, minimizing the risk of voltage fluctuations and providing a stable reference point for the electrical system. Fifthly, documentation and labeling are important for future maintenance and troubleshooting. The separately derived system should be clearly labeled to indicate its source, voltage, and other relevant information. A wiring diagram should be provided to show the connections and grounding scheme. This documentation will help ensure that the system is properly maintained and that any future modifications are done correctly. Sixthly, compliance with local codes and regulations is crucial. In addition to the NEC, local electrical codes may have additional requirements or restrictions for separately derived systems. It is important to consult with the local electrical inspector or authority having jurisdiction to ensure that the installation complies with all applicable codes and regulations. Seventhly, coordination studies are often recommended for larger separately derived systems. A coordination study involves analyzing the electrical system to ensure that the overcurrent protection devices are properly coordinated to minimize unnecessary outages and maximize system reliability. This study can help identify potential problems and ensure that the system is designed to operate safely and efficiently. Eighthly, surge protection may be necessary to protect sensitive electronic equipment from voltage surges and transients. Surge protective devices, or SPDs, should be installed at the service entrance and the downstream panels to divert surge current away from sensitive equipment. The selection and installation of SPD should comply with NEC Article 285. Ninthly, regular inspections and maintenance are essential to ensure the continued safe and reliable operation of the separately derived system. The system should be inspected periodically for any signs of damage, corrosion, or loose connections. Any problems should be promptly addressed to prevent potential hazards. Tenthly, training and education are important for anyone who works on or maintains the separately derived system. Electricians and other qualified personnel should be properly trained in the installation, maintenance, and troubleshooting of these systems. This training should include information on the NEC requirements as well as best practices for safety and reliability. Understanding the implications for the 208 volts panel specifically involves recognizing that this panel, as part of a separately derived system, must adhere to all the aforementioned grounding and bonding requirements. This includes establishing a local grounding electrode system, ensuring that the grounding electrode conductor is appropriately sized according to NEC Table 250.66, and bonding the transformer enclosure and all metallic components to the equipment grounding conductor. Moreover, the overcurrent protection devices on both the primary 480 volt side and the secondary 208 volt side must be properly sized and coordinated to protect the transformer and the downstream loads. In summary, installing a separately derived system, such as a 208 volts panel powered by a transformer from a 480 volt source, requires careful attention to grounding, bonding, overcurrent protection, and compliance with the NEC and local codes. By following these guidelines, you can ensure that the system is safe, reliable, and compliant with all applicable regulations. Furthermore, considering practical aspects such as load calculations and voltage drop is essential for ensuring optimal performance of the separately derived system. Load calculations involve determining the total electrical demand that the 208 volts panel will need to supply. This calculation should include all connected loads such as lighting, receptacles, and equipment, and should take into account any diversity factors or demand factors that may be applicable. Accurate load calculations are crucial for properly sizing the transformer, conductors, and overcurrent protection devices. Voltage drop is another important consideration, especially for longer circuit runs. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, conductors should be sized appropriately, and the length of circuit runs should be kept as short as possible. The NEC provides guidelines for voltage drop in branch circuits and feeders, and these guidelines should be followed to ensure optimal performance. In addition to these practical aspects, it is also important to consider the environmental conditions in which the separately derived system will be installed. For example, if the system is located in a damp or corrosive environment, special precautions may be necessary to protect the equipment from damage. This may involve using corrosion-resistant materials such as stainless steel or coated conduit, and providing additional ventilation to prevent moisture buildup. Another consideration is the potential for electromagnetic interference, or EMI. EMI can disrupt the operation of sensitive electronic equipment and can be caused by nearby electrical equipment, such as transformers or motors. To minimize EMI, shielded cables and enclosures should be used, and the system should be properly grounded and bonded. Furthermore, regular testing and maintenance are essential for ensuring the continued safe and reliable operation of the separately derived system. This testing should include insulation resistance tests, current impedance tests, and overcurrent protection device tests. Any problems that are identified during testing should be promptly addressed to prevent potential hazards. Finally, it is important to stay up to date on the latest changes to the NEC and other applicable codes and regulations. The electrical industry is constantly evolving, and new technologies and standards are being developed all the time. By staying informed about these changes, you can ensure that your separately derived system is always in compliance with the latest requirements. To summarize, Installing a separately derived system requires a comprehensive approach that takes into account not only the basic grounding and bonding requirements but also practical considerations such as load calculations, voltage drop, environmental conditions, and EMI. By following these guidelines and staying up to date on the latest codes and regulations, you can ensure that your system is safe, reliable, and efficient. Another vital element in understanding separately derived systems involves the concept of impedance. Impedance in an electrical circuit is the measure of opposition to alternating current, similar to resistance in a direct current circuit, but also includes the effects of inductance and capacitance. A low impedance ground fault path is crucial for the rapid clearing of ground faults, which minimizes the potential for equipment damage and electric shock hazards. The National Electrical Code emphasizes the creation and maintenance of this low impedance path in separately derived systems. Firstly, the equipment grounding conductor plays a critical role in providing this low impedance path. This conductor, typically a wire or conduit, connects the non-current carrying metallic parts of electrical equipment back to the grounded neutral point of the separately derived system. The equipment grounding conductor must be sized according to NEC Table 250.122, which bases the size on the rating of the overcurrent protection device in the circuit. For example, a 20 amp circuit requires at least a number 12 American wire gauge copper equipment grounding conductor, while a 60 amp circuit requires at least a number 10 American wire gauge copper equipment grounding conductor. Secondly, bonding jumpers are used to connect different metallic parts of the electrical system together, ensuring that they are all at the same potential. This is particularly important in separately derived systems where the transformer enclosure, the service equipment enclosure, and any metallic conduits or raceways must be bonded together. Bonding jumpers must be sized according to NEC Table 250.102, which bases the size on the size of the ungrounded conductors. Thirdly, the grounding electrode conductor connects the grounded neutral point of the separately derived system to the grounding electrode, such as a ground rod or a metallic water pipe. The grounding electrode conductor must be sized according to NEC Table 250.66, which bases the size on the size of the ungrounded conductors. The grounding electrode conductor must be installed in a manner that minimizes impedance, such as by using a direct and unspliced conductor. Fourthly, the grounding electrode system itself must be designed to provide a low impedance connection to earth. This typically involves using multiple grounding electrodes, such as ground rods or ground plates, connected together to form a grounding grid. The NEC requires that the grounding electrode system have a resistance to earth of no more than 25 ohms. If the resistance is greater than 25 ohms, an additional grounding electrode must be installed. Fifthly, regular testing and maintenance are essential for ensuring that the low impedance ground fault path is maintained. This testing should include ground impedance testing, which measures the impedance of the ground fault path from the electrical equipment back to the grounded neutral point. If the impedance is too high, it indicates a problem with the equipment grounding conductor, bonding jumpers, or grounding electrode system. Sixthly, proper installation techniques are crucial for minimizing impedance in the ground fault path. This includes using proper connectors and terminations, avoiding sharp bends in conductors, and ensuring that all connections are tight and secure. Improper installation techniques can significantly increase the impedance of the ground fault path, which can delay the clearing of ground faults and increase the risk of electric shock hazards. Seventhly, coordination with other electrical systems is important for ensuring that the low impedance ground fault path is effective. This includes coordinating the overcurrent protection devices in the separately derived system with the overcurrent protection devices in the upstream electrical system. This coordination ensures that ground faults are cleared quickly and efficiently, minimizing the potential for equipment damage and power outages. Eighthly, documentation and labeling are essential for future maintenance and troubleshooting. The separately derived system should be clearly labeled to indicate its grounding and bonding requirements. A wiring diagram should be provided to show the connections and grounding scheme. This documentation will help ensure that the system is properly maintained and that any future modifications are done correctly. In summary, maintaining a low-impedance ground fault path is crucial for the safe and reliable operation of separately derived systems. This involves careful attention to the equipment grounding conductor, bonding jumpers, grounding electrode conductor, grounding electrode system, installation techniques, coordination with other electrical systems, and regular testing and maintenance. By following these guidelines, you can ensure that ground faults are cleared quickly and efficiently, minimizing the potential for equipment damage and electric shock hazards. Another aspect to consider is the application of specific NEC articles that pertain to separately derived systems. Firstly, NEC Article 250 provides comprehensive requirements for grounding and bonding. This article covers everything from the types of grounding electrodes that are permitted to the sizing of grounding and bonding conductors. It is essential to be familiar with this article when installing a separately derived system. Secondly, NEC Article 450 covers transformers. This article includes requirements for transformer overcurrent protection, transformer location, and transformer ventilation. It is important to comply with this article when installing a transformer for a separately derived system. Thirdly, NEC Article 310 covers conductors for general wiring. This article includes requirements for conductor ampacity, conductor insulation, and conductor installation. It is important to select conductors that are suitable for the application and to install them in accordance with this article. Fourthly, NEC Article 384 covers panel boards. This article includes requirements for panel board overcurrent protection, panel board location, and panel board labeling. It is important to comply with this article when installing a panel board for a separately derived system. Fifthly, NEC Article 700 covers emergency systems. If the separately derived system is used to supply emergency power, it must comply with this article. This article includes requirements for emergency power sources, emergency lighting, and emergency circuits. Sixthly, NEC Article 701 covers legally required standby systems. If the separately derived system is used to supply legally required standby power, it must comply with this article. This article includes requirements for legally required standby power sources, legally required standby lighting, and legally required standby circuits. Seventhly, NEC Article 702 covers optional standby systems. If the separately derived system is used to supply optional standby power, it must comply with this article. This article includes requirements for optional standby power sources, optional standby lighting, and optional standby circuits. Eighthly, NEC Article 705 covers interconnected electric power production sources. If the separately derived system is used to supply power to a utility grid, it must comply with this article. This article includes requirements for interconnection equipment, interconnection protection, and interconnection metering. Ninthly, NEC Article 690 covers solar photovoltaic systems. If the separately derived system is used to supply power from a solar photovoltaic system, it must comply with this article. This article includes requirements for solar photovoltaic modules, solar photovoltaic inverters, and solar photovoltaic system grounding. Tenthly, NEC Article 692 covers fuel cell systems. If the separately derived system is used to supply power from a fuel cell system, it must comply with this article. This article includes requirements for fuel cell modules, fuel cell inverters, and fuel cell system grounding. In summary, compliance with the NEC is essential when installing a separately derived system. It is important to be familiar with the relevant articles of the NEC and to follow them carefully to ensure that the system is safe and compliant. Also, it is very important to remember the following points. 1. Always consult the latest edition of the NEC and any applicable local codes before installing a separately derived system. 2. Hire a qualified electrician to install the system. 3. Have the system inspected by a qualified electrical inspector. 4. Keep the system properly maintained. By following these guidelines, you can ensure that your separately derived system is safe, reliable, and compliant.